Yeah, this is the end, I guess. So 8.5, graphing basic absolute value and quadratic functions. But we've already used this method before. It's just, can you plug in values and then chug away, right? And I got my handy calculator here today, I think. Yeah, so that's what I'm going to be using. Calculator method to do a lot of this work. I don't want to do it by the order of operations. The calculator is going to save me a lot of time. So linear versus nonlinear equations. Linear equations generally look like these top two right here, y equals mx plus b, which we went into. We had pretty much a whole unit on that stuff. In addition to the second one here, which we have is standard form. Of course, this one's slope-intercept. And yeah, the nice thing about these, because the rate of change is constant, because it's a slope, that's all you need is slope and a point, or really slope and y-intercept, not only to write the equation, but to graph these. But any point would do, as we talked about. But now that we're looking at nonlinear equations, such as absolute values or quadratics, and I think we've seen this basic form, right? This trinomial stuff, ax squared plus bx plus c. It's just now it's an equation equals 0. That's a crucial part of that, because when we went over polynomials in that section, we did see equations that were like that. And as long as we can factor these quadratics, we can solve them. If by chance it can't be factored, then I don't think we're going to look at that today, but in a future class you'll look at different strategies for those, because they can always be factored, just sometimes they're not real. Now, unlike linear equations where we just say, hey, I know the slope and I know a point, and I can put the point on the graph and use the slope to find the other points, now we're saying that since the rate of change is going to be changing all the time, we can't actually just do that. What we're going to need is a table, and then we're going to make as many points as we need to see what the pattern is, and then we connect those points. Okay? This table making process right here, that's something that we've been doing with the exponent stuff, right? Like, seems like you've seen some of that 2 to the power of x or something like that. You make a table, and then you put the points on the graph, just connect the points. And the last thing here is, on Canvas, the nice thing is it kind of knows, if I remember right, what the pattern should be. So usually within a couple points, you're in pretty good shape. So absolute value equations. Yeah, for absolute value equations, just so you understand, just kind of the basic format of these, and we're going to pretend like I can draw straight lines right here. But an absolute value graph would look something like this. This is kind of the foundation for our absolute value graphs. And these are supposed to be straight lines, but notice they meet here at the origin. And then it can be shifted. It can be made to be more narrow, or even it could spread out a little bit more. It can move up or down depending on what you choose to do to it. But this is kind of the basic format that we will expect when we see absolute value equations, like in this basic format. Okay. Quadratics, on the other hand, are going to look a little bit more curvy, but they almost take the same shape. So we got x's and y's. So a basic quadratic would look, let's pretend like I drew a good parabola there, but it's called a parabola. I don't think you care, but that's what it's called. And you see how it kind of takes this up, down, then up kind of format, right? Down, then up. See that? It's just this one gets really high, really steep, really fast, usually. Okay, and again, just like with your absolute values, you can kind of spread this out to make it wider. You can make it a little bit more thin in between, more closer together, and you can move it up or down or left and right. Now, mathematically, of course, there's ways to do that, but we're not really concerned about that. As long as you can put these types on graphs, that's all we care about right now. So with this graph right here, we got 4 times the absolute value of x. And whatever you think about this type of equation, remember, it really is y equals 4 times the absolute value of x. So when you go to make your table of x's and y's, like this, and I'm going to give myself enough space for, what is that right there? I got 5. I guess that's about what we've been doing, right? But if I need more, then I can just kind of zoom out and expand this. So I'm just going to go with some values that I guess, like I said, we're kind of familiar with and we've seen quite a bit of. -2, -1, 0, 1, and 2. Now, I know some of you guys are like, well, do we have to include the negatives? Not necessarily, but I think it's very good for us because remember, the basic shape for our absolute value equations is that, yeah, that V type shape, okay? So we need to see stuff not only to the right, which is gonna be a straight line, but to the left as well, which is just a line in the other direction, okay? We should. Well, what happens with this? Remember that we have the equation, no matter which form that you like it in, function notation or just regular equation notation. But now I have a y value, an x value to choose that I've chosen. So this is y equals 4 times the absolute value of x, but I just chose x as 2, right? Sorry, negative 2, thank you. But how far away is negative 2 from 0? It's 2, so that changes now. Notice the parentheses change from an absolute value to a regular parentheses, but absolute values are how far away the number is from 0, it's 2. So that really is 4 times 2, and that's what makes this a positive 8. Now, before I go to the next value, negative 1, I'm going to relate it down here to where the x value is positive 2. Now, I think some of you know where this is going, but remember, y equals 4 times the absolute value of positive 2. So how far away is positive 2 from 0? 2, and 4 times 2 is 8. See how that repeats? So we have these two ordered pairs, negative 2, 8, which I can put on the graph right here. And I've got 2, 8, which is right here. And so that's something you noticed about, hopefully you noticed about the V that I drew on the last slide, is it's kind of like a mirror image of itself. It's a reflection of itself. So if I get a line that's here, it's reflected across the y-axis this way. Okay, so that's why, I think I placed those, that's why these are kind of the same distance away, if I'd drawn them better anyways. They're the same distance from the y-axis, just straight across from each other. All right, so continuing this, now we got, let's go to the negative 1. The x is negative 1, okay? So that's 4 times, it's the absolute value of negative 1. And how far away is negative 1 from 0? It's 1. So that's 4 times 1, which is 4. Okay, so that's negative 1, 4. Now, just what I was just barely talking about with the reflection theme, if I go down here to 1, I'm kind of expecting this value also to be 4. Let's just make sure that it is. Okay, so it's y equals 4 times the absolute value of, now it's positive 1. And 1 is 1 away from 0, so that's just 4 times 1, which is 4. See that? Boom. So we got the points, negative 1, 4, and 1, 4. I made better dots on my line, but that's okay. The last one we got is the x value is 0. So let's see if I can fit that in there. Y equals, it's 4 times the absolute value of 0. Well, how far away is 0 from 0? It's 0. And 4 times 0 is 0. So my corresponding y value is 0, 0, which is at the origin. Okay, now, like we saw on that last slide, we were kind of expecting a V shape. This one's V-shaped, but you see right at the tip of the V, it changes directions. Okay, so this one, I'll try to do this one nice with some technology here. No, that's not what I wanted. I don't know, something like this. See that? But then it changes direction, and then it goes back up here like this, right? And yeah, even though these are lines right here, they'll continue upwards forever. Okay, but this is kind of what we're looking at, and again, if you just kind of thought about this with like a line of reflection right here, some kind of mirror line, this is mirroring itself on the left to the right, or right to the left. All right, here's another absolute value one. So again, just the basic shape should be some kind of V shape, but we got a bunch of other stuff happening to this one, not just something being multiplied by it, but then something being added to it as well, not only on the outside, but then again on the inside as well. Okay, now if you want to rewrite that as y equals that stuff, that's fine. Here's what you should not do is distribute this negative 6. Do not distribute the negative 6, okay? Even though it is, absolute values are considered parentheses, but that's order of operation stuff, okay? So let's go ahead and start with our table. We got x's and y's. And let's hope that, again, this, kind of the same 6 values will work for us. I think that's 6. 6, there we go. right, so let's try the same values. I'll say -2, -1, 0, 1, and 2. Now, it's possible, and that's what I mean by this graphing stuff kind of being just, you just got to keep working at it until it fits in the graph, because it's possible you may put in some x values and it's like, that didn't really work, or it's some kind of fractional value. That's a piece of crap, right? So you'd have to adjust maybe, and it's possible that we may have to adjust this table so that it will fit on the graph. Maybe it's been moved too far up or too far to the left or right or down, who knows? But we're gonna find out, hopefully, with this first value. -2, x is -2. It's kind of a big equation there, but it's it's y equals, it's -6 times the absolute value of x, but now x is -2, plus 1, that's the absolute value, plus 5, okay? I'm going to skip a few steps here just to save myself some space because I'm pretty limited here. But -2 plus 1 is -1, but the absolute value of -1 is 1. Okay, so I got y equals -6 times 1 plus 5. That's -6 times 1 is -6. Then plus the 5 is -1. Okay, so I have this ordered pair, and I could put that on the graph right now, but I want to see what else is going to happen as we move down. In fact, where it kind of reflected on that last one, where it would say -2 is -1, and then maybe 2 would be -1. That's not going to be the case in this one because of all the adding and multiplying and stuff. So let's just go to the next value and see what happens there. Now my x value is -1. So y equals -6 times the absolute value of, now it is -1. But plus 1 plus 5. Absolute value plus 5. Okay, so in that absolute value, I got -1 plus 1, which is 0. The absolute value of 0 is 0 plus 5. So it's really just 0 plus 5, which is 5. So I get a corresponding y value that's 5 right there. -1, 5. All right, fair enough. But what about when the x value is 0? Well, you got y equals -6 times the absolute value of 0 plus 1. Absolute value plus 5. So I'm going to skip probably more steps than I should right here, but right here I'm going to get, this is where I'm going to get -1. Okay, so just with this information, I can see that it's reflecting between these two values, because the y's, where I had a y value that was -1, now I have another y value that's -1. Okay, now hopefully we'll see the significance of that as we move forward. Let's go down, let's set this next one up. Y equals -6, now it's a positive 1, plus 1, plus 5. Okay, so again, I'm skipping a lot of steps here, but the absolute value 1 plus 1 is 2, -6 times 2 is -12, and then plus 5 makes that -7. And that one will fit on the graph, that's nice. What about this last one where the x value is 2? Well, y equals -6 times the absolute value of 2 plus 1, absolute value plus 5. So again, it's skipping some steps there. It'd be -6 times 3, which is -18, plus 5 is -13. That one's not even going to fit on the graph right there. But we can kind of visualize where that'd be. You got 2, -13, way down here. So let's see what happened, what has happened right here. Okay, so we got -2, -1, that's the red point. -2, -1 here. Then we also have -1, 5. That's over here. In purple. And we got 0, -1 right here. And then 1, -7. 1, -7. And that's all I could fit. Now remember, this kind of creates a little bit of a reflection for us. I can't fit 2, -13, although we could visualize it way down here. So the point where this starts to reflect is right here, this purple point. And again, we'll talk about the significance of that. So this is what this graph looks like. Okay, we see the change in direction, starting from this purple point down here. And then it goes back this way like this. And what you notice, or maybe you've noticed, is that it reflects, so it should have gone through this point, at least if I'd drawn it better, it would have. Well, this is not a V. That's true. It's an upside down V. Why did that happen? It's because of the negative 6. The 6 was negative being multiplied by that absolute value, which flipped it. Okay, well, why did it shift to the left? Because we got the plus 1 right there. Why did it shift to the left when it's addition? Don't worry about it. Okay, you'll figure that out in a different class. Well, why is it up here at positive 5? That's because we added 5 on the outside of the absolute value. Okay, so there's little things that we can do to this in order to shift it leftwards or rightwards and then upwards and downwards. Or even the negative 6 kind of made this, I would say that's thinner than what we would have expected in the past, but there you go. That is the graph on this one. On Canvas, it only needs 2 points, even not just for parabolas, but for this absolute value kind of stuff. It looks like it wants this peak value right here, whether the V is up or down. It wants this point, and then any other point would do. So if you can figure out where that peak is, generally it's within these values that we have for our table. I still recommend putting together a full table, because you just never know on an exam when they're going to be like, hey, I need to see 5 points on this sucker, and then what do you do? See what I'm saying? So I still recommend using these just kind of as a foundation. But the more experience you get with these, whether you want it or not, that's what it will take in order to get this down where it's like, I know exactly where this would be and what it would look like. Expand on your question right here. This one is a positive x squared. The coefficient is positive. And we know that this is, it's kind of built like that quadratic stuff. Why? Because it's x squared stuff, so I'm expecting a parabola, but I'm also expecting it to again, I'm saying pointing upwards like this, yeah. Okay, it's just, again, what does this 4 do to it? Because a parabola is going to be a nice little U in there. Well, let's find out with the nice table right here. So if I can set this up. I guess I only need 5 values, whatever, okay? In any case, let me say, let's start with -2, -1, 0, 1, and 2. Then we'll see if we need that extra space right there. But again, these x values, they're just going straight into the equation. And I'm not using h of x just really for space purposes, although you're welcome to if you'd like. Let's start with y equals 4 plus x squared. But now our x we chose is -2. It's squared. And -2 times -2 is 4. That's positive 4. And 4 plus 4 is 8. So we get this ordered pair, -2, 8. Okay, so that's up here. And well, let's see the rest of this graph. Okay, so let's look at -1. What happens to this equation when x is -1? Y equals 4 plus, that'd be -1 squared. And -1 times -1 is 1. So 4 plus 1 is 5. Y equals 5. So we also have this ordered pair, -1, 5. All right, well, what about when x is 0? Well, then you get y equals 4 plus 0 times 0, which is 0 still. But y equals 4 plus 0 is 4. Okay, so we have this ordered pair 0, 4. Fair enough. How about when x is 1? That's positive 1. Y equals 4 plus 1 squared, 1 times 1, which is 1. And 4 plus 1 is 5. So we have this other ordered pair, 1, 5. Now you see this 5 how it repeated? That means that the tip of this thing, also known as a vertex, if you're wondering about that, would be this ordered pair right here. It's the y-intercept for us, okay? Now, is it always going to be the y-intercept? Not necessarily, depending on what they do to the equation. Let's keep going here. Let's look at when x is 2. So y equals 4 plus 2 times 2, which is 4. We've seen that already, right? 4 plus 4, that's going to be 8. So I don't need that. I don't need another point to make this graph work. I have my ordered pairs. I got -2, 8. And we also have that reflection as well, right? We got 2, 8 as well, right there. And then we had -1, 5. -1, 5, and also 1, 5. And then our last point at 0, 4, that's our y-intercept, okay? Now just again, there should be some curvature here. I'm doing this by hand, so it may not be so obvious. But you should be able to see that between these two, like my red and purple point right here, the slope is different than it is between the purple and the green point. So even if you were just like, hey, look, I'm gonna connect these with straight lines, like this, technically you'd be okay. But we want to be a little bit more accurate than that, even though I worry that my drawings make it worse. Here we go, let's try it out. I'll use a black line this time. So, well, see me making it worse. That's okay. Yeah, that wasn't too bad for me. I'll take it. So, for canvas, again, you only need 2 points, and you'll have to choose that you want the parabola function in order to get this on the graph. But one of the points that you have to have is the, again, that's called the vertex, whether you want to call it a vertex, just the tip of the U. Well, how do we know that's the tip? Because it's right in the middle of these points. Even if you said, what number's right between, again, it's 5 and 5, but it's between because it's the X values are different. And then see the Y values here, they're the same. So look at your X values, what number's in between. And since it's 0, it's corresponding Y value. That tells us what the tip is right there. So you guys are gonna try this one. And while you're doing it, I'll make the table and graph, and then we can compare them. But again, the process is essentially the same. All right, so let's go ahead and get these values on. I can't put negative 214 just because the graph, again, is too small, but negative 1.8, that's okay. Right there. We got 0, 4, and we got 1, 2, 2. Now, the other thing here is we got 2, 2 right here, okay? Now, what this means is that if we look, in fact, I'm going to zoom in here on the graph, okay, just between these 2 points. Now, why am I focused on these 2 points? Because they're right next to each other, but they're essentially across from each other. So right in between is where we're going to say that's a line of reflection is. Let me see how I want to word this. That is where the tip should be. Okay, so you see how down here at the bottom that the orange point has a Y value, X value that's 1. The blue point has an X value that's 2. So the tip has to be right here in the middle at 1.5. Okay, 1.5. Somewhere in there. Now, we don't have to actually figure out where that is right now. And as far as I can see, you shouldn't see anything quite like this on canvas. So this is kind of a random example. But we should see that we have a line of reflection there. I guess I'll use red. Right in between these points, okay? So I'm only putting this line here to show that that's where things reflect with this U or parabola, whatever you want to call it. So where the green is about 1.5 way to the left, we should have another 1.5 to the right. And same with the purple as well, it's 2.5, so 2.5 to the right. So that's kind of how I'm making this graph. Where exactly is the tip? I really don't care right now. But in the future, you will. Okay. So let's see if we can put this down. Right. So something like this. Yeah, that's better. And again, where does that actually tip at? I don't know. Pretend like my drawing is good though. Something like this. Okay. Now, even though this is not really on the assignment, I still want you guys to see that the method is the same, right? Whether you use, whatever the equation looks like, you can always use table method to graph. But this reflection thing is kind of crucial. And for the next problem, we're going to see that it's also important if we can see, especially on a graph, where the lines where parabola goes through the x-axis is important. We'll get to that. But if we could have, I was kind of looking in the beginning to see if this equation or this trinomial could be factored. It can't. And this goes back to what we learned about polynomials. Not that I think a lot of us remember that far back, but I remember this polynomial, this one can't be factored. what this is essentially telling us is that it's not going through the x-axis, okay? Meaning that there's no, they're called roots when the parabolas go through this x-axis stuff. This one doesn't have any, which is why this cannot be factored. I don't know, that's not really just kind of a random factoid, because we're going to need that information on the next one. There we go. Yeah, this one says write the equation for this graph. Okay, now this one, it does show us the two roots. Okay, and that's why, again, that's important. We got this root right here, where the x value is 4, that's at 4, 0. And then we got this one right here also, that's right between 8 and 10 would be 9, so that's 9, 0. Now, these 2 points are important. Really, as long as we understand that this is a parabola, it's that U-shaped graph, then we know that we're looking for some kind of equation that looks like what we saw as a quadratic, right? Ax squared plus bx plus c. And yeah, if you wanted to say f of x, that's fine, okay? You can say it equals y as well. I'm going to keep that off for now just so we understand what we should expect to see in the end. Well, how do the roots help us? Because this is actually an equation where we're looking for this quadratic, this trinomial, to equal 0. Well, how are we supposed to remember that? Because the y values in both of these are zeros. Okay? So if I made this equal to y, I just replaced the y with 0. That's all I did. And now I should be ready to write my equation. Well, remember the 0 stuff, okay? Usually, if we saw a quadratic, well, I guess we didn't call them quadratics, but trinomials like this, what we tried to do is split them up into these binomials like this, making them equal 0, right? So if you had x here and x there, maybe it was adding or subtracting. Maybe there's even multiplication there. Then we would make this one, let's say this one, whatever it is, equals 0, but this one also, you know, x minus maybe something equals 0. Then we solve these types. This is just kind of working backwards, okay? Because we just saw that the x value is 4 when y is 0, and the x value is 9 when y is 0. What this does is it says that your x values is 9 and 4. 9 and 4. So we have those two values to work with. I guess I'll move down here. I think I'm over-explaining this, by the way, but we're going to look at two binomials here. And again, it should equal 0, like this, okay? Now, in both of these, yeah, we got the x already set up. But see how that the first one in purple there is x is 4? In order to make it 4, we'd have to make that minus 4. Because remember, if you were to continue solving this one, you'd say, well, make x minus 4 equals 0. Then you'd add 4 to both sides. See what I'm saying? Then you see x is 4. So it's really kind of the opposite of what you see in the root, where this value is positive 4. In the binomial for this one, I'm making it minus 4. And so the same thing is going to happen where the x value is 9. I'm just going to show this as minus 9 right there, okay? Now, that's not really a quadratic formally. That's because we need to multiply those two binomials. So I'd say, look at this. I guess I'll use some FOIL on this one, really just for the sake of space. But x times x is x squared. X times negative 9 would be negative 9x's. Then I got this distribution right here with negative 4 times x, which is negative 4x's. And also negative 4 times 9, which is positive 36. And then, even though that's equal to 0, I'm pretty much ignoring that equal 0 business right there. And I just look to combine my like terms. Negative 9x's minus 4x's, negative 13x's. Of course, I still got the x squared. And also the positive 36. Well, I don't really need that to be equal to 0 anymore. I can just make that equal to, you can make it equal to y. That's okay. You could make it equal to y on the left side as well, if you wanted to, but I ran out of space, so this is it. This is the quadratic, the equation that would create this parabola. But again, the focus really is just the roots. Find the two roots, find the two values, find the two x-intercepts, and then you can easily make your two binomials. You just have to multiply them out in the end.